All right, section 22.9 deals with Hofmann elimination. And you might be looking at that and saying, wait a second, didn't we cover that way back in Organic Chemistry 1? We talked about Hofmann and Zaitsev products. And yeah, we did talk about those, and we're going to talk about it more in this chapter, except now we're going to look at converting an amine into a leaving group. So you might remember that earlier on we talked about how we do an elimination with an alcohol. We could convert it into a tosylate using tosyl chloride and pyridine, and then we could treat that with a base, and we would generate an alkene. And so now what we're going to do is we're going to do something similar with an amine, where we're going to take the amino group, which is a very poor leaving group, and then we're going to convert it into a good leaving group, and that will enable us to do an elimination, and we're going to see that we're going to get Hofmann products predominantly. Now, how do we convert an amino group, which is a poor leaving group, or here it's a bad leaving group? Anyhow, how do we convert a bad leaving group into a good leaving group? Well, if you remember earlier on in this chapter, we talked about exhaustive alkylation using excess methyl iodide, and I just said it alkylates once and it becomes more reactive and does it again and again. Well, here's where it comes up again. Okay, so if you exhaustively alkylate this primary amine that's shown here, you end up with this quaternary ammonium salt. But it turns out that now you've converted your amino group into a good leaving group. So it's got that positive charge on it. It's ready to leave. You see the iodide is the spectator ion here. And so now when we treat this compound or a derivative of this compound with a base, we can do an elimination. Now, the base that's commonly used is not sodium methoxide, is not terbutoxide, is not DBU, is not DBN, is not any of those guys. It's silver oxide, okay? And I'll get into that in a little bit more detail here, but if you want to do a Hofmann elimination of an amine, right, think about it. If you were to eliminate here, you'd get the Zaitsev product, but we're eliminating here to get the Hofmann product. The first thing you would do is treat it with excess methyl iodide, and that would give you this intermediate. So you'd have all those methyl groups, right? And then you have your iodide like this, and then the silver oxide can do the elimination. So that affects the elimination and gives you the Hofmann product. Now, the reason why we use silver oxide is because initially, when you have the quaternary ammonium iodide, it's going to react with the silver oxide to make silver iodide, which is going to precipitate out of the reaction mixture. And so you have hydroxide left over to do your elimination. Now, just to review a little bit, you guys would remember that this is called an alpha carbon. This would be a beta carbon, and then this would be another beta carbon. And you can see the beta carbon in red and the beta carbon in black. They both have hydrogens. But again, when we form that good leaving group from our amine, we see that the Hofmann product is the product that's going to predominate. And so we say that Hofmann eliminations are regioselective for the less substituted alkene, the Hofmann alkene. Now, we're scientists. We have to ask, why is this? Why is it that we end up with the Hofmann product as the major product and not the Zaitsev product as the major product? Well, it goes back to our old buddy Newman, right? The Newman projection. So if you take a look at the Newman projection, so again, be reminded that this carbon that's labeled number 2 here in both of these, this would be our alpha carbon, okay? Now, if we were to use this carbon number 3 as our beta carbon, and we were to do our elimination there to make our Zaitsev alkene, you see that when you draw the Newman projection, you see there's a gauche interaction between the leaving group and the alkyl group that's sticking out here. However, when you do the Hofmann elimination, if we use this still as our alpha carbon, but now if we use this carbon as our beta carbon, you can see that there is no gauche interaction. So this is the key. Here we have a gauche interaction, but here, look at this. No gauche interaction, right? And so that is why the Hofmann product is going to predominate, is just because this leaving group is so big and bulky. Now, I usually don't make my students draw the Newman projection on their quizzes. I just want them to know the concept that when you convert the amine into a good leaving group with exhaustive alkylation and then treat it with a base, it's going to be the Hofmann product that predominates, but the reason why is because there's no gauche interaction during the elimination process. Now, before we move on to trying some practice, okay, there's one more thing I want to remind you of, okay? And it's this term that I don't think comes up a whole lot in Organic Chemistry 2, but it is covered in Organic Chemistry 1. Remember that when you're doing an elimination reaction, okay, if you're doing an E2 reaction like is shown here, that the leaving group and the proton that are participating, so the leaving group and the proton, or the leaving group and the proton, what do you notice? They have to be anti-coplanar to each other. Okay, you see anti-coplanar here and anti-coplanar here. So that is a requirement in order for the elimination to occur. Draw the major product that's expected when each of the following compounds is treated with excess methyl iodide. So that means step 1 is going to be excess methyl iodide, followed by aqueous silver oxide and heat. So we'll just put silver oxide, water, and heat. Okay, so this is going to be a Hofmann elimination, right? So we're talking about Hofmann elimination here. All right, so let's take a look. We got cyclohexylamine. So if we draw cyclohexylamine, okay, this is our alpha carbon. We've got 2 beta carbons. This is a beta and this is a beta, but you can see because of symmetry, those 2 betas are equivalent. And so the only place we can have our elimination is here. So there's no differentiation. There's no Hofmann and Zaitsev. There's only one elimination product. And so we can just write down our conditions. Step 1 is going to be, I'll write out the whole thing. We'll put here excess methyl iodide. That's going to give me my quaternary ammonium salt. So I've got my iodide. There we go. Then in the next step, we're going to treat that with silver oxide, water, and heat. And that's going to give us our cyclohexene in this case. All right, next one is R3-methyl-2-butanamine. So 1, 2, 3, 4, like that. So we got 3-methyl, and if it's R, there we go. So we've got R3-methyl-2-butanamine. If I zoom in here, okay, here's our alpha carbon. This is a beta carbon, and this is a beta carbon. But if I pull off the proton where I have the green beta, that's going to give me the Hofmann product. So the double bond is going to have to be here. And so let's write out our condition. So step 1 is going to be excess methyl iodide. Step 2 is going to be, it's going to be silver oxide, water, and heat. And that's going to give me this compound. So that's going to be 3-methyl-1-butene. And the last one, let me just move it up here a little bit. So we've got NN-dimethyl 1-phenylpropane-2-amine. Okay, this sounds really long here. So let's start with, we've got propane-2-amine. So if we try to draw propane-2-amine, right, just this portion here, you got 3 carbons, and you've got the amine here. And then you've got NN-dimethyl, okay, NN-dimethyl, and then you've got 1 phenyl. So you've got a phenyl sticking off here, like that. Okay, so again, if we zoom in, here's our alpha carbon. This is a beta carbon, and this is a beta carbon, but the beta carbon in blue is going to produce the Hofmann alkene. So let's write out our conditions. If I can squeeze them in here. Number 1, excess methyl iodide, right? If you repeat this enough times, you're going to remember these conditions. Step 2, aqueous silver oxide and heat, and that's going to give me my Hofmann alkene, which is going to look something like that. So there you go. You know, if you practice these enough, eventually you're going to remember all those reaction conditions. All right, so there we go, Hofmann elimination.